complaining about speech and you want an award.
Yeah, I just bought my speech.
Okay, so I updated the grade book. There's a couple of questions I have to regrade on the exam. And so I'll do that, and there'll be some corrections to that. Chapter 9 problems are due this evening or before I get to getting to the scores, which is not going to be midnight. So, and then the other ones are due Friday, chapter 10. From what I can tell, chapter 11 is kind of a mixture of SN1, SN2, E1, and E2. So, my suggestion is if you have questions on those, you can come bring those to class and we can go over them probably on Friday. Because what I plan on doing is we're going to do problems today, and then we're going to finish up these problems on, hold on. There you go. Take this stapled one. Everybody has a stapled one, right? Okay. Because on Wednesday we'll also continue on with some of these problems. What I want to do today with these problems is to kind of go over some of the things that we have to take into account when we're looking at writing E2 reactions. And so I have these I have up through question 9 on the handwritten problems on Top App for you to answer. Okay, so were there any questions about E2 from last week? And this is where we find out. So, under the chapter 11, and this is just where they went. Under chapter 11, I have a whole series of questions, and we'll get through as many of these, and then I'm going to leave the rest of them for you to do for Wednesday. I'll assign them as homework, Bobby. I'll assign them as homework problems so that you can do them. I'm not quite sure if it'll tell you whether you're correct. Well, I think it'll tell you whether you're correct or incorrect, maybe. I don't have a lot of, when I come up with these problems on my own, I don't have a lot of control over giving you multiple attempts. So we'll see what remains. Okay, so we will start with reaction number 1. And reaction number 1 is this molecule. Now I put these on paper so that it's the first question on the paper. So the question is, identify the major products of the E2 reaction. A and B, or part D is no reaction occurs. Okay, has everybody had a chance to answer? I count 29 people, so. All right, let's see what it says. Uh-oh. What? So we've got 14 A's, 8 B's, 6 A and B's, and 1 no reaction. Yeah. Are you sure? Well, I'm going to ask many questions. But, okay. Interesting. So, that problem let me write it out here. Okay, how am I going to solve this problem? Give me some help. What's the first thing I should do? David?
Draw the chair.
No. I don't need to draw the chair structure. Let's do the alpha and beta carbons. So here's alpha, here's beta, there's beta. Okay, so label the alpha and beta carbons. And now what should I do? Josh?
Figure out if those hydrogens are anti-periplanar to the leaving group.
Okay. Figure out if the hydrogens are anti-periplanar to the leaving group. We don't really need to see that the hydrogens are anti-periplanar. What did we say on Friday in terms of rings? The hydrogens that are anti-periplanar to the leaving group in a ring system are the ones that are what?
Trans.
They're trans. So that's why we don't need to put the chair in place, is because we just need to make sure that the beta hydrogens are trans to the leaving group. But I don't see any beta hydrogens. What?
Labels of beta headers?
Well, I don't see any beta hydrogens. They're not there.
You have to draw them in.
Okay, I got to draw them in. So if I have to draw them in, how do they go? Do they go on a bold wedge, dashed wedge, or bond in the plane? Jacob?
Bold because the two other are on gas wedges, so they have to go.
Okay, so I have to put in the hydrogen on a bold wedge. Is that what you were going to say, Carolyn?
Yeah.
Like that. Now, why? Because in a that's a rhetorical question. I'll answer it. Our tetrahedron is set up so that we've got 2 in the plane, 1 bold and 1 dashed. So basically, it's whatever's missing from that cyclohexane ring. So those 2 hydrogens have to go in. So we'll call this one HA. We'll call this one HB, because they basically would lead to products A and B. So they have to go on bold wedges. What?
But it's not trans to, or it's not anti.
So my next question then, is everybody with me so far? So my next question is, can HA be lost in an E2 reaction? No, because it's not trans to the bromine. So I cannot remove HA. How about HB? Can I remove HB? No. So what's the correct answer? No reaction. So it doesn't matter what the base is. It doesn't matter if it was tertiary butoxide or NH2 minus. This is a no reaction as far as being an E2 mechanism. Okay. So kind of notice the steps that we went through here. The first steps, and I'll even write them down. The first steps were to label the alpha and beta carbons. And then secondly, you've got to locate then the beta hydrogens. And if you need to, you might have to put them on a bold or dashed wedge, depending on whether I've shown that to you or not. Then third, what do we do? Very plain. Can each beta hydrogen be removed? Because if it can't be removed in an E2 reaction, then you're not going to get that product. And then once you have the list of the beta hydrogens, that can be deprotonated, then and only then do you look at the difference between the tertiary butoxide and the NH2 minus and apply those rules. Like what hydrogen should be removed from the tertiary butoxide. The ones that are least sterically hindered. The NH2 minus is going to remove the hydrogen to give you the most stable, most substituted product. But notice that's number 4 now. My first 3 steps are to tell me whether the hydrogen can be even removed by the base. So in this case, in this reaction, there's no reaction. Because none of the beta hydrogens are trans to the leaving group. They're both cis. Right, does that make sense to everybody? If it doesn't, you got to say something. Bless you. So every one of these problems is going to have like a new wrinkle to it, maybe. And this set of groups here, I can change the bold and dashed wedges, and I can probably get a good 6 problems out of this. 6 different problems out of just this system. And there's like 9 total, so I can get even more. All right, let's go back here. So if you were the one person that got that right, because that's the way you were thinking, not just because of a guess, a fortuitous guess, then you're in good shape. This morning there was one person as well. And I've been doing this a long time, so I know what problems to start with. Okay? So that's the steps we have to take. All right, so let's apply that to question number 2, wherever it is. Okay, here's question number 2. And notice I can change bold and dashed wedges here. So these problems may look the same, but they can be different. So now what's the major product of this reaction? A and B, or no reaction? And you have all these on paper. I finally realized that it's like, well, by the time everybody writes everything off the screen. Okay. Much better, 93% correct. So what's the major product here? A. Because the hydrogen attached to the carbon of the methyl group is now on a dashed wedge, which makes it trans. The one on the ethyl group is still bold, so it cannot be removed. So the tertiary butoxide will remove a sterically hindered hydrogen if that's all there is. So if there's only one hydrogen that can be removed, that's going to be the major product of the reaction. Okay, good. So let's move to number 3. Okay. So, just to show you how psychic I am, I'm going to predict that C and H are the top 2 answers here. C and H. And they're at 1512. So you know what we need to do? Discuss. Discuss and we'll revote.
Are you wondering like what? Yes. I feel like that'd be in the
Those, the hydrogen.
yeah.
Okay, time to revote. I guess you just have to, if you want to change your answer, you can go ahead and change your answer. If you want to stay where you're at, you can go ahead and stay where you're at. Is everybody done what they need to do? Yes? No? I'll give you another couple seconds. Okay. All right, let's see. "24 C's and now only 5 H's. So you move towards product C. Why was that? Jacob?
Because the carbon is also a bit carbon and it has 20 big hydrogens.
Which carbon?
The one coming off the ring.
The CH3 that's
Yeah.
coming off the ring? Okay.
And it has 3 beta hydrogens connected to it. And one of those is anti-trade planar to bromine.
Okay. So is that the only set of hydrogens that can be removed?
Yeah.
We agree? So in this case, this CH3 are the only hydrogens that can be anti-periplanar to the Levy group. So that's the only possible hydrogen can be removed, and so C is going to be the major product.
But like the hydrogens that are coming off of that CH3, are they also trans? Are they also like on a wedge or a dash? Like
One's on a dash, one's on a bold,
Okay.
one's in the plane. So the thing also with this set of CH3s is they have free rotation because they're not in the ring. So they have free rotation. So not only are there 3 hydrogens that I can orient anti-periplanar to the bromine, but I can freely rotate any of the 3. So those beta hydrogens are able to be removed. So now we've got an additional beta hydrogen to worry about when in a problem like this. Okay. All right, so that's another potential little wrinkle there. Reaction number 4. What do we think about this one? Now I've changed the base to NH2 minus, and it looks like I've kind of changed the stereochemistry. once. Okay, let's see what we've got here. Ooh. We got a bunch of answers. Okay. Discuss.
So, I think we're with the most stable product.
Just make it detached.
No, that's so I was just this one looking more stable because it has that double bond between the I don't know, the only difference is that bigger is to the
We ready to revote? Or not, or keep your answer the same? I'll give you a few seconds to go ahead and, if you want to change your answer or not. Okay. Everybody changed that wants to change? All right, let's see what it looks like. All right, so we got 15 B's, 12 A and B, and 2 A, B, and C. Okay. Well, let's take a look at this one. So, the methyl group is bold, the bromine is bold, the ethyl group is bold, and the CH3 is on the dashed line. And we've got alpha, beta, beta, beta. So we've got beta hydrogen A, beta hydrogen B, and then beta hydrogen C, depending on which one gives each of the products. So my question is, how many of those beta hydrogens can be deprotonated? Can HA be deprotonated? Yes. B? C? So can all three be deprotonated? Yes. What kind of base am I using? I'm using amide, so it's going to produce the product that is most stable, most substituted. So which product is that? Well, A is going to have the double bond there with then the CH2, CH3, so there's product A. There's product B. And there's product C. Which one's most stable? A and B. There's 4 alkyl groups attached to A, 4 4 alkyl groups attached to double bond in B. And how many in C? Just 2. Carol?
So the size of the alkyl groups doesn't matter?
The size of the alkyl groups has never mattered, right? If we think about when we've said tertiary carbocations, did our tertiary carbocation matter if it was methyl groups or ethyl groups? No. And the same thing's true for the double bonds. So the size of the double bond, or size of the alkyl group attached to the double bond does not matter. It just has to be an alkyl group. Josh?
Does that matter if it was the tertiary butoxide or the?
Well, the tertiary butoxide would be a separate problem.
Okay.
So we would need to do that separately.
The next problem.
I know. I know. It may seem like it's total madness, but there is a method, there is a system that's usually in place.
So it doesn't matter whether the beta hydrogens are axial or not?
Axial or not? Well, okay, so if the beta hydrogens, so what would happen in this case is the bromine would have to be axial. And what we would do is we would do a ring flip to get each one of those 2 hydrogens to be axial to then be deprotonated. So that's why we don't have to draw the chairs out. What we know is that in a 1-2 system, if the bromine is axial, then the 2 hydrogens will have to be axial. And so whatever energy it takes for the molecule to go in that position, that's what it will. But the critical thing is only hydrogens that are trans to the leaving group can become axial. So that's why we don't even have to mess with it anymore. Michael?
Like, if you had an ethyl group on a double bond, it would make it more stable because you could push the electron density into the double bond, or is that wrong?
No, it doesn't. The size of the alkyl group doesn't matter when it pushes electron density in. There's no difference between a double bond with 4 methyl groups and 4 ethyl groups. So that's what I was saying. We use that same principle for carbocations. It didn't matter whether the carbocation had an ethyl or a methyl group. So the identity of the alkyl group doesn't matter, but the fact that it is an alkyl group does. Okay. So in this case, we're getting the 2 most stable products, which are A and B. So then, yes, if I'm systematic about the way I go through things, then the next problem should be that same molecule with a tertiary butoxide on it. Doesn't take a lot of creativity. From one molecule, I could change it from a 6-membered ring to a 5-membered ring. Right? Most people would be, it's the same problem. Although some people would be like, oh, it's brand new. So I can do lots of things here. Considering that's what these are the kinds of problems you're going to be answering on the next exam. Okay, going once. Okay, let's see what we've got here. Most popular answer is product C for this one. So if we go back here to the same problem, only now I'm going to change to terse butoxide. The steps don't change. I've got 3 beta carbons with 3 sets of beta hydrogens. Which beta hydrogens can be removed? All of them. So now we take a look at the characteristic of the base. And the terse butoxide can deprotonate the hydrogens that are the least sterically hindered. So in this case, I've got a tertiary, another tertiary, and over here I've got a primary. So the terse butoxide will deprotonate the C hydrogen because it's a primary hydrogen and it's the least hindered. You're good? Okay. So in this case, with terse butoxide, the major product would be C. Okay. So we have to take into account, that those steps, and always go back to the basics on these. First, the first basic would be, what kind of reaction is it? And we know these are all E2s because, well, the question says it's E2, but also because terse butoxide, NH2 minus, immediately tell you that it was E2.
And then also that it's an alkene being produced.
Yes, and it's an alkene, so that's E2 as well.
Will we only see the NH2 minus and the terse butoxide in SN or E2?
Yes.
Okay, and not in E1.
Not in E1. Because these are active bases. E1, it just kind of forms a carbocation, and then the hydrogens leave. But when these guys are there, they're ripping the hydrogens right off. So they're forcing this to be E2. They're forcing it to be bimolecular. All right, then let's see. The last one is... Oh, the last one's a good one. We'll do that. What did I do? Okay, so they all kind of look the same after a while, but you've got to break them down and go through the steps for every one. a couple more seconds. Going once. Okay. All right, we got 21 A's. Really like another answer on here. None of the above. Because actually none of those products would be formed. Because of the CH3. The CH3 should not be there. That CH3 should not be there. When I edited this problem, When I edited the problem, I took the CH3 away from the bromine, but I didn't take it out of the answers. So if the CH3 was not there, A would be the major product of the reaction. Now why? Why'd you choose A over B? But they're both tertiary hydrogens. They're both tertiary. This one's tertiary and that one's tertiary, so they're both tertiary. You're right. But they're both tertiary, but the methyl group's smaller than the ethyl group. So when we're looking at, so with this one, what we're looking at is when you have normally we look at primary versus secondary versus tertiary, but in this case, while these two hydrogens are both tertiary, we can look at their surroundings, and having the methyl group attached to the carbon with that hydrogen is less sterically hindered than having the ethyl group. So that's why A would be the major product. Okay. Okay, so outside of that, so here's what I'm going to do. I'm going to take the rest of these problems and I am going to assign them as homework. And when I assign them as homework, I don't have the option of giving you more than one. Honestly, I don't even know what I'm giving you. If I'm giving you just one shot, if I'm giving you you answer it and it tells you whether it's right or wrong, I have no idea because I don't have the other menu that I normally have. So I'm going to make the rest of these homework. They're in chapter 11, and so you can go ahead and you can do those. These are the remaining ones, and then the first 9 questions on the handwritten problem set. On Wednesday, we will go over the I'll take, if you have questions about these, we can answer them first, and then we'll see if I get the other problems on that sheet into the Top Hat format. And if I do, then you can just answer them on your device. If I don't, then you'll work on them, and I'll walk around and you'll say, hey, I got this for this question. I'll tell you whether you're right or wrong. Okay? So if you have questions, email me or come see me.
I just wanted to let you know that on this exam, this
20's wrong.
20 is wrong.
Oh, never mind. What was your?
Oh, this is added wrong.
It's added wrong.
Yeah, so you gave me
I added.
141. I should have had 131.
Oh, you're gonna be honest.
I mean, I thought about it.
You did.
Yeah,
And you erred on the side of being ethical.
I did.
You'll get a reward for that someday. Remember when you're close to the line at the end of